Hello, in this video I will be speaking about conformations of alkanes. In previous videos it was noted that carbons can rotate around single bonds, so there are a number of different ways that a particular alkane can be arranged by rotating from one conformation to another. And we're going to look at that in more detail in this particular video. So let's review and talk about the kinds of isomers that we've dealt with so far. In this video we're going to be talking about what are called rotational isomers, where you go from one to another by simply rotating around single bonds. These are also sometimes called conformational isomers, sometimes called conformations, sometimes called conformers. So let's start with ethane, and notice that I have a model of ethane here. 2 carbons, 6 hydrogens, 3 hydrogens on each carbon. But notice that you can rotate around that central bond. The structures I have on the screen are just different ways of representing the same structure, ethane. Notice that here's a carbon, and we have the traditional tetrahedral structure. This is what's called a wedge and dotted line diagram for obvious reasons. This is what's called a sawhorse diagram, maybe for obvious reasons, maybe not. But notice again that this is essentially the same as that, just looking at it from a slightly different angle. And then this is what's called a Newman projection, and these are a little bit more arcane, but essentially you're looking at it on end, like this, and notice that there are 3 hydrogens coming out in front towards you. That's these 3 hydrogens on that carbon, and there are 3 hydrogens back behind going away from you. That's these 3 hydrogens. So this is a carbon in the middle, and then behind this circle there's another carbon back there. So this is what's called a Newman projection, named after a person named Newman, obviously. And then we have the ball and stick models, which is there are examples of online that you can see pictures of them. I just made a model of the ethane here. Now these structures all represent what's called the staggered conformation, because if you look down the bond, you'll notice that hydrogen on the front carbon, then hydrogen on the back carbon, then hydrogen on the front carbon, then hydrogen on the back carbon as you go around. So this is what's called a staggered conformation. On the other hand, we have these 3, again a wedge and dotted line diagram, a sawhorse diagram, and a Newman projection. And then this is the model of the ball and stick model of this particular conformation. This is what's called eclipsed, because you notice the hydrogen in front is eclipsing with the hydrogen in back. These two, one is essentially hiding behind the other, just like the moon hides behind the earth when a eclipse of the moon happens. And notice that the hydrogens both pointing straight up are eclipsed with each other, and the hydrogens both pointing to the side here are eclipsed with each other, and these 2 hydrogens are eclipsed with each other, and these 2 hydrogens are eclipsed with each other, and these 2 hydrogens are eclipsed with each other. So this is what's called an eclipse conformation. So eclipsed, staggered. Now, what is the relationship between the staggered and eclipsed forms? Are they real? Do they actually exist? Well, they are. In a real sample of ethane, there would be some of the molecules that would be in this conformation, some of the molecules that would be in this conformation, but they interconvert very easily. So these are conformational isomers as opposed to constitutional isomers, which would be like N-butane and isobutane. We saw those earlier where they have the same formula, C4H10 in that case. But you can't turn one into the other. They're different compounds. You can separate and put them in different bottles, and they don't turn into each other. Whereas with ethane and other conformations, you could, if you even could separate them and put the eclipsed ones into one bottle and the staggered ones into a different bottle, within a split second they would go back to being the mixture that they were before. Some of the eclipsed would turn into some of the staggered, and some of the staggered would turn into the eclipsed. So they are truly in equilibrium. That's why we use this kind of arrows for that. Here's a question. Do they have the same energy? Suppose this has the same energy as this, and the answer is no. The eclipsed form is a little bit higher in energy, and that's because the electrons in these carbon-hydrogen bonds in front and in back are closer together than the electrons are in the carbon-hydrogen bonds in this conformation. And as you know, electrons have the same charge. They're all negative, so they repel each other. So essentially, eclipsed is not as happy as staggered, and so it's higher in energy. So we could put them on an energy diagram. Notice that I have the eclipsed form on top and the staggered form on bottom, and it turns out there's about 12 kilojoules per mole. So if you had a mole of eclipsed ethane molecules and a mole of staggered ethane molecules, this mole would have 12 kilojoules more energy. Now, are there other conformations of ethane besides eclipsed and staggered? And the answer is yes. There's an infinite number where the dihedral angle, that's the angle between a hydrogen on the back carbon and a hydrogen on the front carbon, is 60 in the staggered conformation, is 0 in the eclipsed conformation, but you can have everywhere in between. So all of these different angles constitute different conformations. So there's literally an infinite number of conformations. Of all of those, the staggered is the most stable, and that's because the bonds on the front and the back carbon are as far away from each other as they can possibly be. If you go a little bit this way, they get closer. If you go a little bit this way, they get closer, until you get to the eclipsed form, and that's the highest energy. And then if you want to go on past that, then it starts getting lower and lower and lower again. So as the atoms rotate around the central carbon-carbon bond, the energy increases as it approaches eclipsed, and then continues to decrease as it goes back down to staggered, and so on. So here is a graph that relates energy to time as we rotate around that bond. So it's low when it's staggered, slowly increases until it's eclipsed, and then decreases again until it's staggered, and increases again until it's eclipsed, and so on. Turns out that that is an exact sine wave. Now, what about propane? Let's go to the next most complicated molecule. Notice that it has two carbon-carbon bonds. So this one is constantly rotating, and this one is constantly rotating. All of those are different conformations of each other. So propane has essentially an infinity of infinities of conformations. But let's choose to look down just one bond here. So let's look down this carbon-carbon bond, and notice that we have hydrogen, hydrogen, and methyl on the front carbon. Excuse me, I'm going to hold it this way. Hydrogen, hydrogen, and methyl on the front carbon, and 3 hydrogens on the back carbon. So that would be exactly like this conformation right here. Now what happens as we rotate that back carbon? I'm going to rotate this bond right here. Notice that the hydrogen, this hydrogen right here, gets closer and closer to the methyl group, and then as it continues to rotate, it gets back to staggered again. So again, we have staggered and eclipsed on this bond. Likewise, of course, we have staggered and eclipsed on this bond, and they're not necessarily, one is not necessarily related to the other. But basically, we go from a staggered form to an eclipsed form, and as we go past that, back to another staggered form. And notice that this staggered form is exactly the same as this staggered form, just as in ethane, all the staggered forms are the same as each other, and all the eclipsed forms are the same as each other. The energy difference in propane is about 14 kilojoules per mole between a staggered form and an eclipsed staggered form. A little bit higher in energy than the difference between ethane conformations, because notice that as we approach the eclipsed form, not only are we eclipsing hydrogens with each other, but we're eclipsing a hydrogen with a methyl group, and that's a little bit more repulsive to each other, and so therefore a little bit higher in energy. So as we continue on around, we go from a staggered form to an eclipsed form, to another staggered form, to another eclipsed form, to another staggered form, to another eclipsed form, but all the staggereds are the same as each other, and all the eclipses are the same as each other. So not much more complicated than the situation in ethane. But what about butane? Now if we look at in butane, there are 3 carbon-carbon bonds, all of which are rotating all the time. So there are an infinity of infinity of infinities, so to speak, of conformations for in butane. But the most interesting one is the central carbon-carbon bond. So we're going to look at this carbon-carbon bond right here. We're going to look down that bond, and what I've drawn is, let's do this. The model that I've constructed here has 2 methyl groups eclipsed with each other. That would be represented by this structure right here, where those 2 methyl groups are 0 degrees away from each other in terms of the dihedral angle. Then as we rotate the back carbon, that back methyl group peers out behind like that, just like a person sticking his head out from behind a wall. And then as we continue to rotate that back carbon, the methyl group hides behind the hydrogen. And as we continue to rotate again, it gets down here, and then as we continue to rotate, the methyl group hides behind that hydrogen, and then it sneaks up here behind in between these two, and then finally goes back to the original structure, which I labeled A, and so therefore again it's labeled A here. To find some terms, when you have a situation where two groups have zero dihedral angle between them, like these two methyl groups, obviously these two methyl groups here, that we use the word syn for, S-Y-N, meaning together, like symphony is playing music together. And because these two methyl groups are syn to each other, we refer to this conformation as the syn conformation. So two slightly different meanings of the word. Syn can refer to a relationship between groups on a molecule, and for that matter, these two hydrogens are syn to each other as well. Or syn can refer to, can be sort of used as a name for a conformation. So this is a syn conformation. These two methyl groups, if they're skewed off from each other by 60 degrees in the dihedral angle, that's referred to as gauche, G-A-U-C-H-E. Now it's actually a French word meaning left, like left versus right. Not sure why that's applied to this situation, but it is, and it's pronounced gauche. So two methyl groups who have any two groups that have an angle, dihedral angle at 60 degrees, called gauche. And so this is sometimes referred to as a gauche conformation. Again, slightly different meanings of the word gauche. It can refer to the relationship between two groups, or it can refer to the whole conformation. These two methyl groups, as indicated here, are what are called anti, in other words, straight across. So that would be this conformation in which this methyl group on the front is pointing up, and this methyl group on the back is pointing down. There's a term for that. It's called anti. So those two methyl groups are anti to each other. As for that matter, these two hydrogens are anti to each other. And this conformation then is sometimes referred to as the anti-conformation of butane. Now, notice that as we rotate from an eclipsed to a staggered to another eclipsed to another staggered and so on, the energies are not necessarily the same as each other. So this eclipsed form and this eclipsed form are not the same. So which one would we expect to be higher in energy? Well, the one where the two bigger groups, the methyl groups, are eclipsed with each other, is going to be slightly higher in energy than this one, where a methyl group is eclipsed with a little tiny hydrogen, and the other methyl group is also eclipsed with a little tiny hydrogen. So notice that then that energy. Notice that this one, as we continue on around, is the same as that one, and so those two energies are the same. And then, of course, we go back to the original one where the two methyl groups are syn to each other, and so that's the same energy as that. Now, what about the staggered conformations? Well, one thing to notice, the staggered conformations are always lower in energy than the eclipsed conformations. Eclipsed, no matter how energetic or non-energetic they are always higher than any staggered conformations. But between the staggered conformations, we can compare this one in which the methyl groups are gauche to each other, and this one in which the methyl groups are anti to each other. Which one would we expect to be higher in energy? Obviously the gauche one, because the two bulky methyl groups are closer together here than they are here, so that's a little bit lower in energy than that. And again, notice that this gauche conformation is the same as this gauche conformation, so the two energies are the same as each other. In a real sample of butane, most of the molecules are in these conformations right here. In fact, very few of them are ever in any eclipsed form, because that's just the top of a hill, and there's very few at the very top of the hill. Most of it will be pulled up down here in the valleys, so to speak. Now, try drawing all the staggered and eclipsed forms in order from one to the next, to the next, to the next, to the next. And by the way, you can start wherever you want to, and by the time you go all the way around the dihedral angle of 360 degrees, you'll be back to the original molecule. But it doesn't matter where you start. So try doing it for 2-methylpentane, and pay attention particularly to this bond right here. So the problem is, before we even start rotating, is how do you put the groups onto a Newman projection? So here's the question. First, decide what atom or groups of atoms are attached to each of the two carbons you'll be rotating. So that's this carbon right here. What's attached to it? Obviously a hydrogen and a methyl and another methyl. And this carbon, and what's attached to it? 2 hydrogens and an ethyl. So this whole ethyl group is attached to that carbon. So here are the two carbons that you're being asked to decide what is attached to them. Obviously this carbon has 2 methyls and a hydrogen, as I said. Here's the 2 methyls and the hydrogen on this carbon, and I've chosen to put them on the front. You could just as easily choose to put them on the back. But if we put them on the front, it's 2 methyls and a hydrogen. It really doesn't matter where you put them as long as there's 2 methyls and a hydrogen on this front carbon. So it could be methyl there and methyl there, or it could be methyl there and methyl there, or it could be methyl there and methyl there, and the third one would then be a hydrogen. Then on this carbon, notice that there's 2 hydrogens and an ethyl group, as I said. So we'll need to put them on the model as well. So here they are, 2 hydrogens and an ethyl group on the back carbon. And it's just because I chose this carbon to be on the front, then that carbon has to be the back. And again, the 2 hydrogens and the ethyl group could go on in any particular place as long as they're on these 3 positions. Okay. But let's all work with that particular model then and start rotating. So here's the first one. Then at this point you get to choose 2 things. You get to choose which carbon am I going to rotate, front or back, doesn't matter as long as you're consistent, and use the same carbon throughout. And then you ask yourself, am I going to rotate it clockwise or am I going to rotate it counterclockwise? And again, that's your choice as long as you're consistent throughout. So in this particular case, I've chosen to rotate the front carbon. Notice that the back carbon with that ethyl group pointing down is the same all the way across, the ethyl group pointing down on the back. But the front carbon with these 2 methyl groups is going to rotate. So here we go. If we start with them there and we rotate, I'm going to choose to rotate them clockwise. So they become here and here, and then they become here and here, and then they become here and here, and then here and here, and then here and here, and then here and here, and I'm back to the original molecule that I had over there. Once you've drawn your rotating structures, and most people don't have too much trouble drawing them once they have the groups attached to the proper carbons, and that's the hard part, then rotating them usually isn't too difficult for most people. But then you have to draw an energy diagram and predict relative amounts of each. So notice that we're going to start with 3 eclipse forms, this one, and this one, all higher in energy, and this one, this one, this one, and this one, which of course that's the same as that, all lower in energy, because as I said, all staggereds are always lower than all eclipsed. Second rule, bigger groups want to be farther away from each other. So these 2 groups are going to want to be far away from each other, and so on. Now let's compare. Let's do the eclipse ones first. So here we have a methyl hydrogen eclipsing with a hydrogen and an ethyl eclipsing with a methyl. In this case we have, again, a hydrogen eclipsing with a methyl and a methyl eclipsing with an ethyl. Over here we have a methyl eclipsing with a hydrogen, a methyl eclipsing with a hydrogen, and a ethyl eclipsing with a hydrogen. In this case we don't have any bigger groups eclipsing with each other. In this case we have a methyl eclipsing with a ethyl, which it makes it a little bit higher in energy than F, and B and D, as they turn out, are the same energy as each other. If you look carefully at those 2 structures, you'll see that they're the same as each other. So those 2 are the same energy. This one's a little bit lower, but still higher than any of the staggered forms. And then if we compare the staggered forms, A, C, and E, notice in A we have a methyl and a ethyl gauche to each other. In C we have a methyl and an ethyl gauche and another methyl and ethyl gauche. So that's going to be a little bit higher in energy. And then back to back to E, and we have just 1 methyl and ethyl gauche to each other. So that's back to a little bit lower in energy. In fact, it's the same as B because those 2 are the same as each other. And rule 2A sort of says that the bigger a group is, the more it wants to be away from other groups. So if you have several different big groups, but they're not the same as each other, the bigger it is, the less it wants to be close to another big group. So try drawing all the staggered and eclipse conformations around this bond in this particular molecule, which would be, 3-methylhexane. And I think you should stop the video at this point and do the whole thing, see if you can do it out. Here is the energy diagram, and yours may look different from this because you may have started with a different conformation than I did. And you may rotate in a different direction than I did. You may choose to rotate a different carbon than I did. But essentially you should have these structures in one way, shape, or form. You should have a structure in which you have 2 ethyl groups gauche to each other and a methyl group anti to one of those ethyl groups, and so on. So you can look at these structures. You might want to stop the video and analyze those structures. I'm going to move on. Here's an energy diagram. First I've drawn the eclipsed ones. And this one is actually the lowest of the 3 because no big groups are eclipsed with each other. Here an ethyl is eclipsed with a hydrogen, here an ethyl is eclipsed with a hydrogen, here methyl is eclipsed with a hydrogen. But in this case, we have a methyl eclipsed with an ethyl, so that's higher in energy. And here we have two ethyl groups eclipsed with each other, so that's even higher in energy yet. And then if we compare the staggered forms, here we have two ethyls gauge to each other, and this methyl isn't gauge to anything, so this is at that particular energy. In this staggered form, we have a methyl gauge to an ethyl, so that's a little bit lower in energy than this one. And this ethyl group is just hanging out over here. And then in this one, we have two ethyl groups gauge to each other as we did over here. Notice we also have a methyl group gauge to that ethyl group. So this is higher in energy yet than this one is. But again, all still lower than any of the eclipsed forms. Now we'll draw in the line between them to make it a wave, and we're done.